So we have this formula here, that sine of alpha plus beta was sine, cosine plus cosine sine. If you put alpha equals beta equals theta, we said, same angle, then this becomes sine of 2 theta on the left. Sine, cosine, and cosine sine are the same, just multiplied in opposite order. So there's 2 of those, and you get this identity. Similarly, this one came from the cosine. This is important because this is how you remember these things. You get so many oodles of different formulas. Who can remember them all? But if you remember, just put alpha equals beta in here, you can figure this one out easily, right? Similarly, this one I had cosine of alpha plus beta was cosine minus sine, right? That's why I may have to move the camera. Oops. Yeah. And if you put alpha equals beta equals theta, then you got cosine 2 theta on the left. And this became cosine theta was cosine squared theta, and sine theta became sine squared theta. So you can imagine this one if you just remember this one, right? And figure it out every time. Same thing with tangent here. Since I'm only one thing short, I should put a tangent of alpha plus beta had this formula was tangent plus tangent over 1 minus tangent. So I put alpha equals theta. I've got 2 tangents on the top, right? Alpha equals beta equals theta. I've got tangent times tangent squared on the bottom. So that's where those 3 came from. And we did some problems with those. Now, as you might imagine, if from knowing trig functions of theta, we can know the trig functions of double theta, we can do the other 3's by reciprocals. Why can't we go in the other direction, start with double theta, go backwards in these formulas and get theta? And we can. Now we can get half angle formulas by letting 2 theta equals alpha, supposed to be alpha on here, and thereby then theta is 1/2 alpha, dividing both sides of these by 2, in equations 2 and 3. Let's start with 2. Suppose I do that in here. In equation 2, if I replace 2 theta with alpha, this becomes cosine alpha. And cos equals cosine squared. And let's see, theta is 1/2 alpha. And sine squared of 1/2 alpha. Place the sine squared theta. There it is. Cosine alpha equals cosine squared 1/2 alpha minus sine squared 1/2 alpha. Now I have a half angle formula, right? If I know cosine and sine, I really just want one trig function of 1/2 alpha, don't I? So what can I do? See where I can go with this? Suppose I use the Pythagorean identity, right? By the Pythagorean identity, I recall that sine squared of any angle, let's say 1/2 alpha, plus cosine squared of any angle is 1, right? Let's just put theta. Theta is 1/2 alpha. Sine squared plus cosine squared equals 1. Then I subtract sine squared from each side. I write equivalently, cosine squared can be replaced with 1 minus sine squared. So I could replace this by the Pythagorean identity, solve for cosine squared with 1 minus sine squared. So let 2 theta equal alpha in this equation. You get a half angle equation. Replace cosine squared with 1 minus sine squared by the Pythagorean identity. And get equivalently now, cosine alpha equals 1 minus sine squared minus another sine squared is 1 minus 2 sine squared. Now I've got a formula that just has sine of 1/2 alpha. I can solve for sine of 1/2 alpha. What I'll do, algebra, I'll add 2 sine squared over to this side, subtract cosine from that side, and get 2 sine squared of a half alpha plus on this side by adding it to both sides equals 1 minus, and I subtracted cosine alpha from both sides. I get a little algebra rearranges it like that. Even though I want to ask you to reproduce this proof, I think it's really useful for seeing where these things came from. Now divide it by 2, and I get equivalently sine squared of a half alpha is 1 minus cosine alpha all divided by 2. I've almost got a half angle formula. I got a formula for sine squared of a half alpha. But if sine squared equals this number here, it follows that sine is plus or minus the square root, right? Just like if you write x squared equals 4, what are the solutions? X can be square root of 4, or it can be minus square root of 4, right? Because this root sign means the non-negative number that has that square, but there's two numbers, one with a plus and one with a minus. Plus or minus 2 are both solutions. Same thing here. If sine squared is this number, sine can be plus or minus the square root of this number, right? So plus or minus square root 1 minus cosine alpha over 2. There's the formula I wanted. Formula 4, we'll call that. That's our first half angle formula. The sine of half an angle is plus or minus square root of 1 minus the cosine of the whole angle all divided by 2. That's the first half angle formula. I think it's you want to see where this comes from, even if I won't ask you to reproduce this. Similarly, also by 2, with, just as before, 2 theta equals alpha is a half alpha. I get, just like I did here, cosine alpha equals cosine squared of a half alpha minus sine squared of a half alpha. So I'll start with that same formula at the double angle formula. Cosine 2 alpha is cosine squared minus sine squared, and then I'll cosine 2 theta is cosine squared minus sine squared. Replace theta with a half alpha to get this. And now this time I'm going to replace sine squared with 1 minus cosine squared, also by the Pythagorean identity. Now what I've got equivalently is cosine alpha equals cosine squared minus a minus cosine squared is 2 cosine squared minus 1. You subtract the 1, and you subtract and subtract the cosine squared to get another cosine squared. So I have proved this is the case. This is an identity. Except this is alpha over 1/2 alpha, sorry. Then the object is to solve for cosine 1/2 alpha. I'll have a half angle identity for cosine. So I'll add 1 to each side and get 1 plus cosine alpha on the left equals 2 cosine squared of a half alpha on the right. Okay, divide by 2. 1 plus cosine alpha over 2 is cosine squared a half alpha. Equivalently, if cosine squared is this number, cosine can be either plus or minus the square root. So I'll switch the sides and square root. And then I've got cosine of a half alpha, the square root of the right, is plus or minus the square root of the left. 1 plus cosine alpha. There it is. This will be equation 5, the half angle formula for cosine. But both of them come from that double angle formula for cosine. These are really useful in higher mathematics. You'll see them a lot. All right, so now we can do the tangent. Tangent will be a little easier to derive. Finally, The easiest, there are more formulas for these half angle identities and for the double angle identities, but the easiest one for tangent is just to do this. Tangent of a half alpha, I can compute this way. Suppose I just take tangent of any angle is sine over cosine of that same angle, right? And I have half angle formulas for sine and cosine. So I'll take this one, plus or minus square root 1 minus cosine alpha over 2, and plus or minus square root 1 plus cosine alpha. We're getting lots and lots of identities. The way to memorize these things is to memorize them in group. Remember the sum and difference identities, you can memorize them in pairs, and they were easier because you just changed all the pluses to minuses and minuses to plus. So you only had to memorize 3 sum and difference identities, then to switch the plus or minuses got you the other 3. That's all you had to do. Similarly, in double angle formulas, I guess you can't see them online quite. All you did was plug in alpha equals beta equals theta, and you got these 3. So all you have to do is really memorize those first 3 sum and difference formulas. Then the next 3 come by switching the pluses and minuses. The next 3 come by putting alpha equal beta equals theta. And now you've got all those memorized practically for memorizing 3. Alas, we're running into a little trouble here. The sine formula is not so easy to memorize. You just have to memorize this half angle identity. See how long the proof was? You can't do that every time. So memorize sine of a half alpha is plus or minus square root 1 minus cosine alpha over 2. But then once you've got that, look how easy the cosine formula is. What's the difference between the sine formula up here and the cosine formula down here? Not much, right? Just change the minus to a plus. So if you know the sine one, change minus to plus and get the cosine half angle formula. And then here's the beauty of it too, right? And from algebra, you know you can write the quotient of the square roots as the square root of a single quotient. Top one over the bottom one. All right? And these are both denominators, so they cancel. And we find out the tangent of a half alpha is just square plus or minus the square root of 1 minus cosine alpha over 1 plus cosine alpha. There it is. This will be formula 6. This one's not so hard to memorize either because it's just the quotient of these two cancel the 2's. So that's what I did when I was a trig student, at least. There are other half angle formulas for tangent that are kind of nice too, occasionally useful. But this one's so much easier to memorize. It's just the quotient of these two cancel the 2's. I like memorizing that way. I can do it, right? I don't keep forgetting all the time. So there's the tangent of a half alpha formula. And now we have 3 half angle identities. The last 3, again, we'll do by reciprocals. We won't memorize 3 extra ones for those. And now we're ready to start all sorts of homework problems here. Here's the first thing. Now by 4, 5, and 6, provide an alternative to what we did before. To evaluating any trig function of a multiple of 15 degrees. Pi over 12. So that's the first application, is you can do these another way, but it's going to do more than that for us, right? Here's an example. Suppose I wanted to evaluate, for instance, this is an easy one, the cosine of 15 degrees, let's say. Before, how did I did it? I'll say recall, this is the previous method. How did we do this before if we wanted the cosine of 15 degrees? Just wrote any multiple of 15 degrees is a difference of special angles. Remember that? And then you can apply the sum or difference identity. So I'm going to do that. I'm going to write this as cosine 45 degrees minus 30 degrees. I'm just reviewing here. And the difference formula, if I call this alpha and beta, we still got our difference formula up there. Cosine of the difference is cosine, cosine minus sine, cosine, cosine plus sine, sine. I guess I didn't write the difference formula, just the sum. So it's cosine, cosine plus sine, sine for the cosine of the difference. Each of these angles in order, 50, 45, 30, 45, 30. And now from the 45, 45, 90, and 30, 60, 90 triangles, I probably remember that cosine of 45 degrees is square root of 2 over 2, as is sine 45 degrees. We did these before. I won't write these again unless you ask me to. Cosine of 30 degrees turned out to be square root of 3 over 2, and the sine of 30 degrees turned out to be a half. I just had to add those half numbers, or those numbers. Square root 2 times square root c, 3, right? Product of square roots is the square root of the product. Times 2 on the bottom gives me 4. Square root 2 times 1 over here, and 4 on the bottom here. So they have a common denominator, they add the numerators over the common denominator. There's what we got before. The claim is now that we have half angle formulas. This might be preferable in some circumstances, right? We'll use equation 5 here now. Half angle for a cosine. Now, alternatively, suppose we want the cosine of 15 degrees. We recognize that 15 degrees is half of a special angle. And we'll write it that way, 1/2 of 30 degrees. On formula 5 for the cosine of half an angle with alpha equals 30 degrees, I'll say this is plus or minus the square root of 1 plus cosine of the whole angle all over 2. There's the formula for the half angle formula, right? So it's with alpha equals 30 degrees. And now cosine 30 degrees is 30 degrees is a special angle, so I can take its cosine. Remember that's square root 3 over 2? This is plus or minus square root 1 plus square root 3 over 2 all over 2. There's an exact representation for calculating the cosine of 15 degrees. I'm going to take a point off on the test for that, though, because we're not simplifying. Why is that not simplified? I've got a quotient within a quotient, right? I've got a compound quotient. So I want to get rid of it. How can I get rid of this compound quotient? How's it run? You could with a little work, yeah. I was going to suggest this, which amounts to the same thing. You can make a common denominator and then try and combine the numerators and denominators. Alternatively, multiply top and bottom by the least common denominator in these secondary quotients, which is 2. In other words, multiply top and bottom by 2. 2 times the top will get rid of the denominators on the top. 2 times the bottom, there's nothing to get rid of, so it's still okay. And now I've got plus or minus square root of 2 plus square root 3 on top. 4. And now square root of the quotient is the quotient of the square root. So this is plus or minus square root 2 plus square root 3 all over square root 4 is 2. Oh, wait a minute. Is it plus or minus? What do I know? Look back to the very first thing. You're taking cosine in quadrant 1. It's positive, right? All trig functions are positive in quadrant 1. So I'll pick the plus. Right? So you have to figure out from the quadrant of the original angle, not this one. Sometimes this one will fool you. Use the original angle. The cosine in the first quadrant is positive, and I'll use that. Look at the very first trig function. There it is, and I'm all smiles until I recognize, wait a minute, I didn't get the right answer. This is the nasty thing about these square roots and why we demand you rationalize them is they can be equal and they don't look the same. These actually are equal. They just don't look like it, do they? Oh, they look very different, but what you do is run this in your calculator, get a decimal, run that on your calculator, get a decimal. This is actually okay, it just doesn't look okay. So this is okay. Just looks different. In fact, there are some ways you can do this. One thing you can do is square both of them. Since they're both positive and you square them and you can see it's the same, you can recognize them being the same. That takes a lot of work. And what you're really interested in is rewriting this in a simpler way. You don't like square roots of square roots maybe, but the algebra for doing that is such a mess that most books and I will just leave it here. So this will be okay. And you can leave your answer with a square root of a square root. I'll accept that rather than do the, what happens is on a lot of these they reduce and a lot of them they don't. And you do a lot of work trying to reduce them and then find out sometimes they don't. It's very depressing. So let's not be depressed. We'll just leave it like that. All right. I don't want to make this an algebra class anyway. So you can put it in either form, and now the half angle or the sum and difference formulas can be used to calculate any trig function of a multiple of 15 degrees. And the reason it works here is every multiple of 15 degrees, its double angle is a multiple of 30, so it's a special angle, right? I can do bigger angles, right? Suppose I wanted to compute the tangent exactly of 195 degrees. Uh-oh. I wonder what the tangent of 195 degrees is exactly. Can I do it? Exactly? Sure I can. 195 degrees is 180 plus 15. Any angle that's 15 a multiple of 15 from an axis is a multiple of 15 itself. So this will be a multiple of 15. Or you can check those rules, divisible by 3, divisible by 5, or there's lots of ways to do this. But I'll say I know I can do this because it's a multiple of 15. Now I can use the sum and difference formulas, or I can write it as half of a special angle. I write this as tangent of 1/2. Double that be 390 degrees. Right? And now all coterminal angles have the same 6 trig functions, right? So what would be an easier way to write this? Would be this. Now, actually, let's leave it that way. Let's leave it that way for now. I'll do it the next step. Tangent of 1/2 an angle alpha by our formula 6 for the tangent of half an angle is plus or minus. Oh, what's that terrible formula? Oh, I remember. It's just the sine divided by the cosine half angle formula with the 2's canceling. 1 minus cosine alpha is 390 degrees, the whole angle, over 1 plus cosine 390 degrees. Right? The quotient of the sine and cosine formulas for half an angle. And now if I want to evaluate the cosine of 390 degrees, what's an easy way to do it? Now I'm going to say all coterminal angles have the same 6 trig functions. So I could just say by coterminal angles all having the same 6 trig functions. I can also write this much easier as 1 minus cosine 30 degrees. Just take 360 out of there over 1 plus cosine 30. How easy. Now I got an easy job, right? And is it plus or minus? Oh. It's tricky, actually. You look at 390 degrees, what quadrant is that in? That's in quadrant 1, right? So you might say, go with quadrant 1, but actually what you're interested in is this original thing. You're trying, the final answer goes by whether this is positive or negative, right? The square root means the non-negative number has a square, so this is always non-negative. You put a plus if this is going to be plus, a minus if this is going to be minus. Look at the very first one. This is in quadrant 3. In quadrant 3, tangent is positive, right? So I'm going to use the plus because this is quadrant 3, and I'll ignore this one. This one's over, 390 is over in quadrant 1 where it turns out tangent is positive. But sometimes you'll get this one as negative, And this one's positive. You want to go with whatever the final answer is supposed to be. Look at this one. Get the plus sign. So now I've got square root of, and cosine 30 degrees is square root 3 over 2. Okay, memorize that one, huh? Once again, I've got compound quotients. This is going to be 2 points off here if you leave it here in algebra. Algebra on these is often harder than the trig. Right. I'm all done with the trig, but I've got some steps here. Let's see, am I still on enough? I guess I'm going off. Talk to me online if I get too far off here. So I've got square root of 1 minus root 3 over 2 over 1 plus root 3 over 2. To get rid of the compound quotients, I'll multiply top and bottom by 2. That'll get all those nasty denominators out of there. They're all the greatest common denominator is 2. And now I have square root of 2 minus square root 3 on top over 2 plus square root 3 on the bottom. There it is. There's an exact answer. Am I done now? And as I took 2 points off here, that's only 1 point back. I got rid of the compound quotients, but now what do I have? I said radicals inside radicals is okay for this class. But I still have a radical in the denominator, right? I don't want radicals in the denominator. So how do I get rid of that one? Well, I got you guys stumped today, don't I? I should have given extra credit problem. Remember conjugates, A plus B square root C, B square root C, and A minus B square root C are called conjugates. That when you multiply one by the other, the radicals fall out. What I do, and this is what makes the algebra the hardest part of these problems, many of them, is take the quotient that you have. Right, there's what I have. Multiply the top and bottom by the conjugate of the denominator. You're trying to get rid of the radicals in the denominator, so use the conjugate of the denominator, 2 minus square root 3, and multiply top and bottom by the same, so you don't change the quotient. And that'll get rid of the radicals in the bottom. Now, sometimes this will simplify a lot. It just depends. On the bottom now, what do I have? 2 times 2 is 4. Then minus 2 square root 3 and plus 2 square root 3 cancel, right? I FOIL. This times this is 4. This times this and this times this outside and inside cancel. And then root 3 times minus root 3 is minus 3. And what do I have on the top? I can multiply it out, but even easier, I could call it 2 minus square root 3 squared, right? It's the square root of the square, right? Just the original number. So on top, I just have 2 minus square root 3. Ooh, easy. On the bottom, I just have 1, right? Square root of 1 is 1. So there's what I've got. This actually simplifies to 2 minus the square root of 3. Who wants that answer when you write 2 minus square root of 3? That's why it's 2 points off, right? So many of these will simplify quite a lot. There's the tangent exactly of 195 degrees in terms of radicals. One more thing I was going to say, and I can't remember now, but we'll use these things to get rid of radicals from the denominator. Now we can go another step here and say, what about sine of 7.5 degrees? Maybe I can do that one, can I? This is the kind of question I'd like to ask you in the test, but I'm not going to, but I sure would like to. because this will really test your skills whether you know this or not. Why do I know I can do 7.5 degrees? It's because it's half of 15 degrees, which we already did. What you're recognizing now is if I can do 30 degrees, I can use the half angle formula like I did with cosine there. I guess you can't see that line yet, sort of. By a half angle formula, I can do cosine of 15 degrees. Once I can do that, I can do any trig function of half of that, or half of that, or half of that. What happens is these calculators that you have these days will do these 15-degree angles if you buy the expensive ones that do exact trig functions, and you can check all your answers on the test. But I want you to do them by hand when I ask you for a cosine of 15 degrees or tangent of 195. Because in the end, you want to be able to do these too, and the calculator won't do this one nicely. But you should be able to when you get out of the class. I just don't want to ask those yet. Everybody will fail, right? If I make you do these twice. But the point is, this is half of 15 degrees, and there's a formula for a sine of half an angle. If I call this alpha, sine of 1/2 alpha is plus or minus the square root, and plus or minus just depends on what quadrant you're in. 1 minus cosine of the whole angle, 15 degrees, all over 2. But wait a minute, I just did cosine 15 degrees. That's square root of 2 plus square root 3 all over 2, and then this whole thing over 2. So this is previous example. So the point is, once I can do half of one angle, I can do half of that, and half of that, and half of that. Half of any angle I want. Like if I want to do sine of 22.5 degrees, I can do that now because it's half of 45 degrees. So not only can I do any multiple of 15 degrees, I can do a whole lot of angles. Anything is half of a special angle, or half of that, or half of that I can now do. And this is a mess. Since it's the first quadrant, we'll put plus, right? This is a sign in the first quadrant. Everything in the first quadrant is plus, so I'll just put plus. And I'll put dot, 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 algebra. I don't want to have you do this on the test. So what I'll do is I'll give you the 15-degree ones and say, do them by hand and show me the work. Otherwise, I'm going to have to ask you these on the test, right? And I'll give you another warning too. When you go to check this with your fancy calculator that checks all those 15 degrees, it won't give you the exact answer. It will give you only the decimal. Can you imagine why? I wanted to make a comment to this effect sometime in the course for people who bought those because they're a math major or engineering or physics major or something and need them. Computing science probably needs them too. Why wouldn't it give me an exact answer for sine of 7.5 degrees when it can? And it can be programmed to. If I can do it by hand, somebody could program it up, right? What happens on these calculators is the second you put in a decimal point, it assumes it's a rounded number. So if you do this on your calculator, if you take, put in square root 2 on one of these fancy calculators, guess what it'll give you back? Square root 2, because it's the exact answer. Square root 2 is square root 2. If you want the decimal, what can you do? You put square root of 2 point. Now it'll give you 1.41415, other stuff. Anyways, it starts off like that. It's non-repeating though. If you want the decimal form on any of those calculators, there is an approximation mode where it will do decimal every time, but who wants that? You need exact answers too often. There's an exact mode, but then it won't give you decimals. So there's another mode that's standard for it. Will give you the best of both. If it can do exact, it will do exact. So you can put in square root 2, but it'll leave it at square root 2. Won't give you the decimal. But if you put square root 2 point, you do that. Sometimes I forget to put in the decimal point. And then what do I do if I get this answer? After I get the answer back, I just multiply it by 1 point. And it says, oh, this is a rounded number, and then it gives me the decimal. So anytime you get the exact answer on your expensive calculator and you want the decimal, just multiply it by 1 decimal point, and it will convert it to decimal immediately. Or you can set it in approximation mode if you want everything in decimal. But that's what's going to happen here. When I take sine of 7.5 degrees, it's going to interpret this as a rounded number. It will only give you a decimal answer. Maybe if you put in this, sine of 15 degrees over 2, it might give you the exact answer. That's just a warning on those calculators. When you're checking your answer, try this. It might give you the exact answer, but you might just have to check this by hand on some of these. Again, I'll try not to give you these on the test. I want to give you the easier ones and pass the class. But the idea is you can do these when you need to. Okay, look at this one then. This is 7A on the homework. This is one of the more tricky ones, I think. Suppose that tangent x is minus 4/3. Fine, this is just part of 4A. What is the exact value of sine x over 2? We wrote last time that if you knew one trig function in a quadrant, I need to put this here, this is in quadrant. X is in quadrant 4. If you knew the quadrant and one trig function, you knew all 6 trig functions. And so you could do all the double angles of trig functions, right? The way you did that last time, you said, suppose I know one trig function of x, sine x equals 0.1 or whatever, and I want to find tangent 2x. How did I do that? Remember this from last time? We did these problems. How did I find tangent 2x? If I'm given a trig function of a double angle, I just immediately write the formula. 2 tangent x over 1 minus tangent squared x. Now I only need tangent, but from the sine I can find the cosine. I can find all 6 trig functions, just plug it in. So I'll say cosine is, if I know, say it's quadrant 1. Cosine is square root 1 minus 0.1 squared, right? Is square root 0.99. And then tangent is sine over cosine. Cosine is 0.1 over square root 0.99, and I just put that in for tangent, and I can compute whatever this is. So that's what we did for double angles. If we're getting a trig function in a quadrant, we recall before, we can get all 6 trig functions using the Pythagorean identities, like we calculate cosine here. Then we can calculate all the double angles using double angle formulas. This is the same thing. Given one trig function in a quadrant, you can find all 6 trig functions, and then find by the half angle formulas, trig function of any half angle. Instead of writing the double angle formula immediately, you write the half angle formula immediately. Plus or minus square root 1 minus cosine x over 2 by equation 4. So you write that. Now I just have to find cosine x from this one, and I can, right? Given a trig function in a quadrant, I know all 6 trig functions. I just have to go solve for them, right? So I'm going to erase this and just say this is analogous to the double angle thing. Trig function in a quadrant, you find all 6 trig functions and plug it into with the double angle formula. Trig function in a quadrant, you find all 6 trig functions, plug it into the half angle formula. So let's see what the other trig functions are. I think I've got room over here. If tangent equals minus 4 over 3, how can I find sine and cosine and all the other ones? I picked this one because it's the hardest. Remember how to find all 6 trig functions if you're given tangent in a quadrant? Tangent and cotangent are the 2 hard ones. Put it here. I'm running out of room over there. I'm going to do tangent. Just took your test. You guys are experts on this. You write it as a point on the unit circle. You root some square of these numbers. Square root of plus or minus doesn't matter because it's squared. Minus 4 squared plus 3 squared is square root of 25 is 5. Right? It's 3, 4, 5 triangle. And you divide top and bottom by that. You write this as minus 4/5 over 3/5. Just divide top and bottom by 5. Or you can take minus that, plus 4/5 over minus 3/5. Right? You say, wait a minute, quadrant 4 This quotient is supposed to be for tangent y over x. Quadrant 4, y is negative and x is positive. That's right for quadrant 4. This is over in quadrant 2. So this, once I write tangent as a quotient of points on the unit circle, I know immediately, therefore, the top one is sine x is minus 4/5. Cosine x is plus 3/5 in quadrant 4. So given tangent, I compute sine and cosine this way. Then I get the others all by reciprocals, right? Cotangent is the quotient of tangent. Cosecant, the reciprocal of sine, and secant, the reciprocal of cosine. Well, that's what you do if you're given tangent or cotangent. Write this quotient by dividing by the root sum square. Get the sine and cosine from it. So I know cosine. Now I can finish this. That's what you do in the half angle things. Given a trig function in a quadrant, find the trig function at half angle. Write the half angle formula. From this, compute the trig function you need, cosine in this case. Just plug it in. So I'll plug this into here now, and I've got plus or minus square root 1 minus cosine is 3/5 all over 2. And then is it plus or minus? It's tricky. It's actually tricky here. Let me move this over just a bit. You say, oh, quadrant 4, let's see. The sign in quadrant 4 is negative, right? Wait a minute. I want the sine of x over 2. That's not in quadrant 4, right? X is in quadrant 4. X over 2 is what I need. So it has this trick. You go back and look at the original angle. In quadrant 4, x is between 270 and 360, right? So divide through by 2, and x over 2 is between 135 and 180. It's actually in quadrant 2. In quadrant 2, a sign is positive, so I want to choose the positive sign. Told you these are tricky. I want, right, I want the sign of x over 2. X over 2 is in quadrant 2. So it's positive. All right, even though x was in quadrant 4. Now what I need to do is just reduce this, right? It's square root of, how do I reduce 1 minus 3/5? Well, you learn your algebra in this class, right? To subtract quotients, you rewrite them as a single denominator. This is 5/5 minus 3/5. Common denominator. Then you subtract the numerators. 5 minus 3 is 2 over the common denominator, 5. And then 2 on the bottom. And how do I carefully do these? Quotient of a fraction divided by a whole number. Right, the bottom one is a fraction 2, 2 over 1, right? Then I'll take top times bottom, 2 times 1 over 5 times 2. 2's now cancel. It's 1 over square root of 5 is what I get. There it is. If the tangent of x is minus 4/3 and x is in quadrant 4, then the sine of a half x is 1 over square root of 5. And similarly, whenever I'm given a trig function of quadrant, I can find all 6 trig functions. I can find all 6 trig functions of a double angle. I can find all 6 trig functions of a half angle. Just write the formula down for half angle or double angle. Find the trig functions you need by previous methods and plug them in. Okay. That's pretty much what I wanted to do today. I do want to mention one more thing here that you should be aware of. This comes out of one of the previous problems. This occurs quite a lot in the sciences. A lot of you maybe science majors of some sort or another. These can be used to simplify trig expressions. One of the things the whole chapter about is proving new identities and simplifying expressions you have. Science, all the time, you're getting complicated expressions like this. Suppose I want to simplify sine of 3x times the cosine of 3x. Maybe I want to simplify it so I can graph it. What a mess that must be, right? It's a wave times a wave. What does a wave times a wave look like? Maybe it's a big jumble, right? How can I simplify that? The trick is to recognize that it looks like something you've seen before. What does that look like? Reminds me of what? Sine times cosine. I remember this one. Sine 2 alpha is 2 sine alpha cosine alpha. Right? And we said, be careful on these. Don't pull the 2 out, rewrite the trig identity here. This was our equation 2. Double angle formula for sine. That looks almost the same. There's just a 2 here that's not here. So what can I do? I can fix it. I can take this one and write a 1/2 times 2 sine 3x cosine 3x. And now by the double angle formula, calling this alpha and this alpha, right? 2 sine alpha cosine alpha is sine 2 alpha. So this is 1/2 sine of twice alpha is 3x. Right? 2 sine alpha cosine alpha is sine 2 alpha, where alpha is 3x. Now you simplify that, that's 1/2 sine 6x. That's not a jumble at all. What is that? Easy as pie to graph, right? Too full of puns here. This is an a sine bx minus c plus d, and c and d are 0, so there's not even a shift, right? The shift point is 0. This has amplitude 1/2, right? Absolute value of a is unflipped. And the period is 2 pi over 6, pi over 3, right? 2 pi over b. But it looks just like this. It goes up and down between y equals plus and minus 1/2. Starting at the origin because it's unshifted with period pi over 3. So it goes like this and this and this and returns to pi over 3. And then it, of course, continues on forever. But there's the graph of this thing. Who would guess you multiply 2 sine waves, a sine and a cosine, and you just get a single sine wave? It's one of the amazing things about trig functions that sometimes books don't point out. They're just, I don't know if they're so interested in doing a formula, but this is a really beautiful thing. You multiply 2 of these things together as long as they have the same angular frequency, right? So it's 3x and 3x in both of them. You just get another sine wave. It gives you a wave again. It's kind of a pretty amazing property. We're going to see some more of these next time. I think we're about out of time today. Yeah. But it's pretty amazing that you can put these things together in big jumbles, and sometimes these trig identities reduce them to a single wave and remarkable property, and it plays into electronics engineering where you've got currents that are coming together and making a joint current that's just a wave. Right out of 7.3 then, problems 1 through 6. Make sure you can do all of those, the double angles and the half angles. And we'll pick up a little bit at the end here next time out of those sections. All right. Thank you for coming in. Hope you have a good weekend again this weekend.